In this example of an axially loaded system, we have a rigid bar A, B, C, D. We have a flexible rod over here attached at A that's vertical, and we have an applied load out at the tip D. The lengths here are that from A to B is 23.5 centimeters, and from B to D is 73 centimeters. You're given some of the material and mechanical properties associated here with the various pieces, but the big key is that we're asked to find two different things. One, what is the load out here at the tip that's going to cause this rod over here at A to yield? And then the second part is, well, what's the displacement at D at this tip when that occurs? And so again, the key is that this bar is rigid. This is actually a beam ABCD, but we're going to ignore its own deformations. It will rotate up on this pivot, but the only thing keeping it in place from spinning freely with the applied load is this extensible rod over here attached at A. Right, so we're going to put all the various things together, and that is that the flexibility of the system or the stiffness of the system is coming from this rod. Remember that axially loaded systems can be captured in their force deformation relationship, with their axial deformation is equal to the axial force times the length over the cross-sectional area of the member and the modulus of elasticity of the member. That's an important thing to keep in mind. There are special conditions under which we're doing the analysis, and that is that we're bringing this rod to its yield stress, so that gives us some critical pieces. And let's put it all together. First, with the free body diagram. We've got the load P out at the far right. Again, special condition, that's P sub Y. That Y stands for yielding, not for the vertical direction, but for the yielding of something in the system. And then we have our reactions at B, and there possibly could be two at one of the X and the Y. And then, of course, with the given system, if it's going to rotate in the direction of the load, we're going to have a system that will rotate like that. It will extend the rod at A, meaning that rod at A is going to want to pull back on the beam, and there is your axial force that we've got here in our rod. We might call that N sub Y since we're at yield. Right? We're asked to find the limiting load, so under that condition, Ny, of course, we said that rod has yielded. That will be given us by the yield stress times the cross-sectional area of the rod. And since the axial stress at yielding is 2 megapascals, and the area is given to us by 2 square millimeters. Remember that there is 1 Newton per square millimeter per 1 megapascal. So those cancel out, and the millimeters will go away, and then that will be equal to, ultimately here, 4 newtons in the member itself, the rod itself. Then by equilibrium, then we know if we sum moments about point B, let's take clockwise as positive, then we'll have a minus 23.5 centimeters times our N sub Y, which we now know is 4 newtons, plus then P sub Y for the yielding times its moment arm of 73 centimeters. Set that equal to 0 because we are at equilibrium, and we will then therefore find that our P sub I is going to work out to 1.288 newtons. That's our limiting force. Right? So if we apply that force out here at the tip at D, we will cause yielding to happen back here at A. Then we're asked to find the displacement that corresponds to that particular situation. So let's draw a displacement diagram. Here's the original position of the rigid bar. C is kind of an irrelevant point here. It's useful for another problem that is very similar to this one, where other things are attached there, but not in this problem. And let's draw what the displaced shape of the system is. And note that what we're going to do, even though each point is going to actually swing in an arc, these angles are actually going to be so small that we're going to ignore that arc, and we'll assume that this triangle is not really an arc, it's rather instead a right triangle. And we'll keep the original dimensions here along the base of these triangles. Yes, that is not exactly correct, but to a first order approximation it actually works out sufficient. And we'll see what the magnitudes of these are at the end of this and see how small this really turns out to be. So notice that what we're trying to calculate is the delta D out here at the tip corresponding to the yielding that's happening at point A. And so the displacement that happens at A in this case is being caused entirely by the elongation of that rod. Now it won't always be like this, but it is certainly the case in this instance that will turn out to be where we're at. So delta B, capital delta B, the displacement at B, sorry, that is not at B, that's at A, is equal to the elongation of the rod at A, and that's equal to the force in that member times the length of that member divided by A divided by E. Now N over A was specified to be at the yield stress, so we don't have to calculate that individually. We can go right at that is equal to 2 megapascals. N over A is. The length of that rod in the original problem statement is 15 centimeters, and then divide by our modulus of elasticity of 6,000 megapascals. Notice the units are going to work out to be length units like they should. And we then discover that our delta A is, well, I'm not quite sure what it is. Let's calculate it. We got 2 times 15 divided by 6,000, and so it's equal to 0.005, and that would be 0.005 centimeters. Let's keep track of those units carefully. And then by congruent triangles, recognize that rigid bar, not bending but rather just rotating, means that by similar triangles, or congruent if you like that better, then we know that delta D is equal to, well, we got to get, delta D is much larger because it's much further away. It's 73 over 23.5 times delta A. That's just the similar triangles at work. So we have 73 over 23.5 times what we found out was delta A, 0.005. And we get then a calculated value of 0.0155 centimeters, which is a very small number, a little bit easier to rewrite this in terms of that delta D is 0.155 millimeters for that answer. Before we found out that PY was 1.228 newtons, not really any reason to write it out with that much precision. Pragmatically, that's about 1.2 newtons. And there is your answer.